800 amp feeders in the same conduit represents a serious safety hazard and violates the National Electrical Code, or NEC. The operation of the compressors at 335 amps for extended periods exceeds their rated capacity and creates an overheating risk. The presence of two different power supplies in the control panel without proper labeling is a potential shock hazard. It is critical to take immediate safety actions. Firstly, isolate and lock out the 800 amp feeders until they can be properly installed. Secondly, derate the compressors to their rated capacity of 274 amps or install larger conductors to handle the actual load. Thirdly, label the control panel clearly to indicate the different power sources. A comprehensive electrical system assessment is necessary. Hire a qualified electrician to conduct a thorough inspection of the entire electrical system. Identify and document all code violations, safety hazards, and areas for improvement. Develop a plan to address the findings and bring the system up to code. Electrical system redesign may be required. Design a new electrical system that meets the National Electrical Code and provides adequate capacity for the plant's current and future needs. Install new conduits, conductors, transformers, and other equipment as necessary. Upgrade panels and switchboards to handle the increased load. Safety training and procedures are essential. Train plant personnel on electrical safety best practices, code requirements, and emergency procedures. Establish clear work instructions and lockout-tagout protocols. Provide safety equipment and ensure regular inspections and maintenance. Management support and communication are also key. Communicate the findings and recommendations to plant management clearly and concisely. Emphasize the importance of safety and the potential consequences of non-compliance. Secure funding and resources to implement the necessary improvements. The fatal incident should be thoroughly investigated to determine the root cause and prevent similar occurrences in the future. Consider hiring a consultant to provide expert advice and guidance on electrical safety and system design. Stay up to date on industry best practices and National Electrical Code revisions to ensure ongoing compliance. The issue of the 800 amp feeders running each phase in the same conduit, specifically 3 conduit runs of 2.5 inches, poses a significant problem. According to the National Electrical Code, conductors of the same circuit must be run together in the same raceway or cable to minimize inductive heating and voltage drop. Separating the phases into different conduits creates an imbalance in the magnetic fields, leading to inductive heating of the conduit and increased impedance, which reduces the system's efficiency and increases the risk of conductor insulation failure. This setup violates NEC section 300.3b, which requires all circuit conductors, including the grounding conductor, to be installed in the same raceway or cable. The solution involves rerouting the conductors so that all phases of each 800 amp feeder are in the same conduit. The conduit size must be appropriate for the number and size of conductors, considering the National Electrical Code's fill requirements outlined in Chapter 9, Table 1, and the conductor and capacity rating factors as specified in 310.15. The 2 solar compressors, each with a 250 horsepower motor and a service factor of 1.15, present another set of concerns. The motors are rated at 274 amps at 460 volts, but they are running at 335 amps for substantial periods. This overload condition can significantly reduce the lifespan of the motors and increase the risk of failure. The service factor of 1.15 indicates that the motor can handle 115% of its rated load for short durations, but continuous operation at 335 amps, which is approximately 122% of the rated current, exceeds this limit. This situation violates NEC 430.32, which protects motors against overload. To address this issue, firstly verify the actual load requirements of the compressors. If the compressors genuinely require 335 amps during normal operation, the motors are undersized and need to be replaced with larger ones that can handle the load without exceeding their service factor. Secondly, if the high current draw is due to inefficiencies or mechanical problems within the compressors, these issues should be addressed to reduce the load on the motors. Thirdly, Ensure that the motor overload protection is correctly sized according to NEC 430.6, 430.31 and 430.32. The overload protection should trip before the motor is damaged by the excessive current draw. The power factor ranging from 87 to 89% indicates that the electrical system is not efficiently utilizing the supplied power. A low power factor results in increased current flow for the same amount of useful power, leading to higher energy costs and increased loading on transformers and conductors. Utilities often charge penalties for low power factors. To improve the power factor, install power factor correction capacitors at the motor terminals or at the main distribution panel. Capacitors provide reactive power, which reduces the amount of reactive power that the utility must supply. This correction improves the power factor, reduces the current flow, and lowers energy costs. The size of the capacitors needed depends on the amount of reactive power required to bring the power factor up to an acceptable level, typically 95% or higher. An electrical engineer can perform a power system study to determine the appropriate capacitor size and placement. The control panel with two different supplies, 480 volts and 120 volts, not marked, is a serious safety hazard. Without clear labeling, personnel working on the panel may inadvertently contact the wrong voltage, leading to electric shock or equipment damage. This violates NEC 110.22, which requires all electrical equipment to be clearly labeled to indicate its purpose and voltage. To rectify this, firstly, clearly label all voltage sources and components within the control panel. Use permanent labels that are easily visible and understandable. Secondly, install barriers or partitions to physically separate the different voltage sections within the panel. Thirdly, provide appropriate overcurrent protection for each voltage system. The fatal incident that occurred on third shift underscores the urgent need for a comprehensive safety review. The incident should be thoroughly investigated to determine the root cause, including whether electrical hazards contributed to the accident. The findings of the investigation should be used to implement corrective actions and prevent future incidents. This may involve revising safety procedures, providing additional training, and upgrading equipment. Regular safety audits and inspections should be conducted to identify and address potential hazards before they lead to accidents. Lockout-tagout procedures must be strictly enforced to ensure that equipment is de-energized before any maintenance or repair work is performed. All employees should be trained on the proper lockout-tagout procedures and their responsibilities. The lack of electrical reference books in a plant indicates a lack of emphasis on electrical safety and code compliance. Invest in a complete set of National Electrical Code books and other relevant electrical standards. Make these resources readily available to all maintenance personnel. Encourage employees to attend training courses and seminars on electrical safety and code compliance. This will help them stay up to date on the latest requirements and best practices. Given the age and condition of the electrical system, it may be prudent to consider a complete system upgrade. This would involve replacing old and outdated equipment with new, modern components that meet current safety standards. A system upgrade can improve reliability, reduce energy costs, and enhance safety. Engage a qualified electrical contractor to perform a detailed assessment of the electrical system and develop a plan for the upgrade. Regularly inspect electrical equipment, including transformers, switchboards, panel boards, and wiring for signs of wear, damage, or overheating. Replace or repair any defective equipment promptly. Keep electrical rooms clean and free of obstructions. Ensure that there is adequate ventilation to prevent overheating. Implement a preventative maintenance program to regularly test and maintain electrical equipment. This can help identify and address potential problems before they lead to failures or accidents. Verify the grounding system's integrity throughout the plant. A properly grounded system is essential for protecting against electrical shock and preventing equipment damage. Test the grounding system regularly to ensure that it meets the requirements of the National Electrical Code. Grounding electrodes, grounding conductors, and bonding connections must be properly sized and installed. Surge protection devices should be installed to protect sensitive electronic equipment from voltage surges caused by lightning or other electrical disturbances. Surge protection devices should be installed at the main service entrance and at individual equipment locations. Regularly test surge protection devices to ensure that they are functioning properly. Arc flash hazards should be assessed, and appropriate arc flash protection should be provided. This may involve wearing arc-rated clothing, using insulated tools, and implementing arc flash safety procedures. An arc flash study should be conducted to determine the potential arc flash hazard levels at different locations in the plant. Warning labels should be posted to alert personnel to the arc flash hazards. The coordination of overcurrent protective devices, such as circuit breakers and fuses, should be reviewed to ensure that they provide adequate protection against overloads and short circuits. A coordination study should be conducted to determine the appropriate size and settings for the overcurrent protective devices. The goal is to ensure that the overcurrent protective devices trip in a coordinated manner to minimize the extent of any electrical fault. Regular testing of overcurrent protective devices should be performed to verify that they are operating correctly. Infrared thermography can be used to detect hotspots in electrical equipment, which can indicate loose connections, overloaded circuits, or other problems. Infrared thermography scans should be performed regularly to identify and address potential issues before they lead to failures or accidents. The results of the infrared thermography scans should be documented, and corrective action should be taken as necessary. All electrical work should be performed by qualified and licensed electricians. Ensure that electricians are properly trained and experienced in the type of work they are performing. Verify that electricians have the appropriate tools and equipment for the job. Do not allow unqualified personnel to perform electrical work. Maintain accurate and up-to-date electrical drawings and documentation. This documentation should include single-line diagrams, panel schedules, and equipment specifications. Keep the drawings readily available for reference. Update the drawings whenever changes are made to the electrical system. In summary, addressing the electrical issues requires a multifaceted approach that includes immediate safety actions, a comprehensive assessment, system redesign, enhanced safety training, and strong management support. Prioritizing safety and adhering to the National Electrical Code are essential for protecting personnel and preventing accidents. By implementing these recommendations, a plant can create a safer and more reliable electrical system.